Hello and welcome. In this video, we will explore the topic of improper integrals, a key concept in the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to define and identify improper integrals, evaluate them using limits, and understand the conditions for their convergence. We will also tackle some advanced problems, including Gabriel's horn, and work through several IB-style practice questions. First, let's define what makes an integral improper. There are two main types. An integral is improper if the function being integrated approaches infinity or negative infinity at one or more points within the interval of integration. This is often due to a vertical asymptote. For example, consider the integral of 1 over x squared from -1 to 2. The function 1 over x squared is discontinuous at x equals 0, which lies within our interval. As x approaches 0, the function's value approaches infinity. This makes the integral improper. The second type of improper integral involves an infinite interval of integration. This occurs when one or both of the limits of integration are infinity. In this course, we will primarily focus on the second type, specifically integrals of the form from a to infinity. So, our main focus will be on integrals where the upper limit is infinity. Now, how do we evaluate these integrals with infinite limits? We use the power of limits. We define the integral from a to infinity of a, f of x dx as the limit, as b approaches infinity, of the definite integral from a to b of f of x dx. This means we first evaluate the integral over a finite interval, and then we see what happens as that interval becomes infinitely large. Let's visualize this. Imagine a function f of x that is positive and approaches the x-axis as x gets large. The improper integral represents the area under this curve from a to infinity. We can approximate this area by taking the integral from a to some finite value, b. As we let b grow larger and larger, the area we're calculating gets closer and closer to the total area under the curve. If this limit exists and is a finite number, we say the integral converges. If the limit does not exist or is infinite, we say the integral diverges. A crucial condition for an improper integral of this type to converge is that the function f of x must approach 0 as x approaches infinity. If the function doesn't go to 0, the area under it will just keep growing without bound. So, for the integral to converge, the limit of f of x as x approaches infinity must be 0. This is a necessary condition, but as we'll see, it's not always sufficient. Let's work through an example to see this in action. We will evaluate the integral from 1 to infinity of 1 over x cubed dx. Our goal is to evaluate this improper integral. First, we rewrite the integral using the limit definition. This becomes the limit as b approaches infinity of the integral from 1 to b of x to the power of -3 dx. Next, we find the antiderivative of x to the -3. Using the power rule, the antiderivative is -1 over 2x squared. Now we evaluate this antiderivative at the limits of integration, b and 1. This gives us the limit as b approaches infinity of -1 over 2b squared minus -1 over 2 times 1 squared. Let's simplify this expression. This simplifies to the limit as b approaches infinity of -1 over 2b squared plus 1/2. Finally, we take the limit as b approaches infinity. As b gets infinitely large, 2b squared also gets infinitely large. Therefore, 1 over 2b squared approaches 0. The limit is 0 plus 1/2, which equals 1/2. Since the limit is a finite number, 1/2, we say the integral converges to 1/2. This means the area under the curve y equals 1 over x cubed from 1 to infinity is exactly 1/2. Let's investigate the integral of x to the power of p from 1 to infinity. This is a very important family of integrals. We're going to analyze the integral from 1 to infinity of x to the p dx. First, let's consider the case where p is greater than or equal to 0. If p is 0, the integral is of 1 dx, which is x. As x goes to infinity, this goes to infinity. If p is positive, say what or 1, the integral of x dx is x squared over 2, which also goes to infinity. In fact, for any p greater than or equal to 0, the function x to the p does not approach 0 as x approaches infinity. Therefore, the integral must diverge. Now let's consider the case where p is less than -1. Let's write p as -k, where k is greater than 1. The integral becomes the limit as b approaches infinity of the integral from 1 to b of x to the -k dx. The antiderivative is x to the -k plus 1 divided by -k plus 1. Evaluating this from 1 to b gives us this expression. Since k is greater than 1, -k plus 1 is negative. This means b to the power of -k plus 1 is 1 over b to the power of k minus 1. As b approaches infinity, this term goes to 0. So the limit is 0 minus 1 over -k plus 1, which simplifies to 1 over k minus 1. This is a finite number, so the integral converges. Finally, let's look at the special case where p equals -1. The integral is from 1 to infinity of 1 over x ddx. The antiderivative of 1 over x is the natural logarithm of x. Evaluating this gives us the limit of ln b minus ln 1. Since ln 1 is 0, this is just the limit of ln b. As b approaches infinity, ln b also approaches infinity. So this integral diverges. This is a very important result. The function 1 over x approaches 0 as x approaches infinity, but not fast enough for the area under its curve to be finite. This shows that the condition lim x equals 0 is necessary but not sufficient for convergence. To summarize our investigation, the integral from 1 to infinity of x to the p dx converges if and only if p is less than -1. It diverges for all other values of p. Let's tackle a more complex example that requires integration by parts. We will evaluate the integral from a to infinity of x times e to the -x dx. Our task is to evaluate this integral for any constant a. First, we set up the limit. This is the limit as b approaches infinity of the integral from a to b of xe to the -x dx. The integral of xe to the -x requires integration by parts. We use the formula integral of u dv equals uv minus integral of v du. Let u equal x, so du is dx. Let dv equal e to the -x dx, so v is -e to the -x. Applying the formula, the integral becomes -xec to the -x, minus the integral of -e to the -x dx. Now we substitute this back into our limit expression and evaluate it from a to b. This gives us the limit as b approaches infinity of the antiderivative evaluated at b, minus the antiderivative evaluated at a. Let's rearrange the terms. We can group the terms with b and the terms with a. This simplifies to e to the -a times the quantity a plus 1 plus the limit as b approaches infinity of -b minus 1 all over e to the b. The limit term is an indeterminate form of type infinity over infinity, so we can use L'Hopital's rule. Taking the derivative of the numerator and denominator, we get the limit of -1 over e to the b. As b approaches infinity, this limit is 0. Therefore, the entire integral converges to e to the negative a times the quantity a plus 1. This is our final answer. The integral converges for all real values of a. Now for a classic and counterintuitive problem, Gabriel's horn. Gabriel's horn is a solid of revolution formed by revolving the curve y equals 1 over x, for x greater than or equal to 1 about the x-axis. We are asked to prove that the area under the curve y equals 1 over x is infinite, but the volume of the horn is finite. Let's start with the area. The area is given by the improper integral from 1 to infinity of 1 over x dx. As we saw in our investigation, this integral diverges. The limit of ln b as b approaches infinity is infinity. So the area under the curve is indeed infinite. Now let's find the volume of the horn using the disk method. The volume is the integral of pi times the radius squared. Here the radius is the function I equals 1 over x. So the volume is the integral from 1 to infinity of pi times 1 over x squared dx. We can pull the constant pi out of the integral. This gives us pi times the limit as b approaches infinity of the integral from 1 to b of x to the -2d. The antiderivative of x to the -2 is -1 over x. Evaluating this from 1 to b, we get pi times the limit of -1 over b plus 1. As b approaches infinity, -1 over b approaches 0. So the limit is pi times 1, which is pi. The volume of Gabriel's horn is exactly pi cubic units. This is the paradox. We have a solid with an infinite surface area, but a finite volume. You could theoretically fill the horn with a finite amount of paint, but you could never paint its entire surface. This demonstrates the power and sometimes counterintuitive nature of improper integrals. Let's look at another type of improper integral, where the function has a vertical asymptote within the interval of integration. This is called a singularity. We'll consider the integral from 0 to 2 of 1 over the square root of x dx. The function 1 over root x is undefined at x equals 0, which is our lower limit of integration. To handle this, we use a limit, but this time the limit is on the lower bound. We define this as the limit as a approaches 0 from the right side of the integral from a to 2 of x to the -1/2 dx. The antiderivative of x to the -1/2 is 2 times x to the 1/2, or 2 root x. Evaluating this from a to 2 gives us the limit of 2 root 2 minus 2 root a. Now we take the limit as a approaches 0 from the right. As it gets closer to 0, root a also gets closer to 0. So the limit is 2 root 2. This integral converges to 2 root 2. What if the singularity is in the middle of the interval? For example, the integral from -1 to 2 of 1 over x squared dx. The singularity is at x equals 0. We must split the integral into two parts, one on each side of the singularity. For the original integral to converge, both of these new integrals must converge. Let's evaluate the first one. This is the limit as b approaches 0 from the left of the integral from -1 to b of x to the -2 dx. The antiderivative is -1 over x. Evaluating this gives the limit of -1 over b plus 1. As b approaches 0 from the left, b is a small negative number, so -1 over b approaches positive infinity. This integral diverges. Since one of the parts diverges, the entire integral diverges. We don't even need to check the second part. Let's work through a few more IB-style examples to solidify our understanding. First, let's evaluate the integral from 1 to infinity of 1 over x times the natural log of x squared dx. This integral has two issues. The upper limit is infinity, and the function is undefined at x equals 1 because of the ln x term. We must split it. We'll split it at a convenient point, say x equals e. This gives us two improper integrals. Let's evaluate the first part. We'll use the substitution u equals ln x. If u equals ln x, then do is 1 over x dx. When x is 1, u is u. When x is e, u is 1. The integral becomes the integral from 0 to 1 of 1 over u squared do. The antiderivative is -1 over u. Evaluating this gives the limit of -1 plus 1 over a. As a approaches 0, this goes to infinity. The first part diverges. Since one part diverges, the entire integral diverges. We don't need to evaluate the second part. Let's try another one. Evaluate the integral from 0 to infinity of x e to the -x squared d. We'll use the substitution u equals -x squared. If u equals -x squared, then do is -2x dx. So x dx is -1/2 do. When x is 0, u is 0. When x approaches infinity, u approaches -infinity. The integral becomes the integral from 0 to -infinity of e to the u times -1/2 do. We can flip the limits of integration by changing the sign. This is 1/2 times the integral from -infinity to 0 of e to the u do. Now we use the limit definition. The antiderivative of e to the u is e to the u. Evaluating this gives 1/2 times the limit of 1 minus e to the a. As a approaches -infinity, e to the a approaches 0, so the limit is 1/2. This integral converges to 1/2. Let's recap what we've learned today. We defined improper integrals as those with infinite limits of integration or infinite discontinuities. We learned to evaluate them using limits, and we saw that an integral converges if its limit is a finite number and diverges otherwise. We also discovered that the condition lim EIx equals 0 is necessary but not sufficient for convergence, as demonstrated by the integral of 1 over x. Finally, we explored the fascinating paradox of Gabriel's horn, which has infinite area but finite volume. You are now equipped to tackle a wide range of improper integral problems. To help you master this topic, I've prepared 5 practice questions in the style of the IBAA-HL exam. Work through them carefully and then check your solutions. Here are your practice questions. Pause the video and try to solve them on your own. Question 1 asks you to evaluate the integral from 2 to infinity of 1 over x to the 4th dk. Question 2 asks for the area under the curve y equals 1 over 1 plus x squared from negative infinity to infinity. Question 3 is the integral from 1 to infinity of e to the negative x ddx. Question 4 is the integral from 0 to 1 of 1 over the square root of 1 minus x squared dx. And question 5 is the integral from 0 to infinity of xe to the negative x dx. Welcome back. Let's go through the solutions together. For question 1, we use the limit definition. The antiderivative of x to the negative 4 is negative 1 over 3x cubed. Evaluating this from 2 to b and taking the limit gives us 1 over 24. For question 2, we split the integral at 0. The antiderivative of 1 over 1 plus x squared is arctan x. Evaluating the limits gives us pi over 2 plus pi over 2, which is pi. For question 3, the antiderivative of e to the negative x is negative e to the negative x. Evaluating the limits gives us 0 plus 1 over e, which is 1 over e. For question 4, we have a singularity at x equals 1. The antiderivative of 1 over root 1 minus x squared is arcsin x. Evaluating the limits gives us pi over 2 minus 0, which is pi over 2. For question 5, we use integration by parts. The antiderivative is negative x e to the negative x minus e to the negative x. Evaluating the limits gives us 0 minus negative 1, which is 1. I hope this video has helped you understand improper integrals. Keep practicing, and you'll master this topic. Thank you for watching. Let's look at a more advanced problem from the IB curriculum. We'll evaluate the integral from ln root 3 to infinity of 1 over e to the x plus e to the negative x dx. This problem requires a clever substitution. The key is to multiply the numerator and denominator by e to the x. This transforms the integrand into e to the x over e to the 2x plus 1. Now we can use the substitution u equals e to the x. If u equals e to the x, then do is e to the x dk. The integral becomes the integral of 1 over u squared plus 1 du. The antiderivative of 1 over u squared plus 1 is arctan u. So the antiderivative is arctan of e to the x. Now we can evaluate the improper integral using our antiderivative. This is the limit as b approaches infinity of arctan of e to the b minus arctan of e to the power of ln root 3. Let's evaluate the limits. As b approaches infinity, e to the b also approaches infinity, and arctan of infinity is pi over 2. For the lower limit, e to the ln root 3 is just root 3, and arctan of root 3 is pi over 3. So the value of the integral is pi over 2 minus pi over 3, which equals pi over 6. This integral converges to a finite value. Let's tackle another IB-style problem. We need to find the total area between the curve f of x equals e to the negative x times sine squared x and the x-axis for x greater than or equal to 0. The function e to the negative x is always positive, and sine squared x is also always positive. Therefore, the function f of x is always positive, and the area is simply the improper integral from 0 to infinity. Our goal is to evaluate this integral. To integrate sine squared x, we use the double angle identity. Sine squared x equals 1/2 minus 1/2 cosine 2. Substituting this into our integral gives us 2 parts. The integral becomes 1/2 times the integral of e to the negative x, minus 1/2 times the integral of e to the negative x cosine 2x. The first part is straightforward. The integral of e to the negative x is negative e to the negative x. Evaluating the limits gives 1. The second part, the integral of e to the negative x cosine 2x, requires integration by parts twice. This is a standard technique for integrals of this form. After 2 applications of integration by parts, you'll find that the integral is equal to 1/5. The details are a bit long for this video, but you can work them out on your own. Now we evaluate this from 0 to infinity. As x approaches infinity, e to the negative x goes to 0, so the first term is 0. At x equals 0, sine is 0 and cosine is 1, so the second term is negative 1/5. The result is 1/5. Finally, we combine the 2 parts to find the total area. The area is 1/2 minus 1/10, which equals 4/10 or 2/5. This is a great example of how multiple integration techniques can be combined to solve a single problem. Let's look at a problem involving the gamma function, which is a generalization of the factorial function. The gamma function, denoted by the Greek letter gamma, is defined as the integral from 0 to infinity of x to the n minus 1 times e to the negative x dx. First, let's evaluate gamma of 1. Setting n equals 1. We get the integral from 0 to infinity of e to the negative x dx. The antiderivative is negative e to the negative x. Evaluating the limits gives 1, so gamma of 1 is 1. Next, we need to prove a recursive relationship. Gamma of n equals n minus 1 times gamma of n minus 1. We'll use integration by parts on the definition of gamma of n. Let u equal x to the n minus 1 and dv equal e to the negative x dx. Then do is n minus 1 times x to the n minus 2 dx, and v is negative e to the negative x. Applying integration by parts, we get this expression. Let's evaluate the first term, the limit term. As x approaches infinity, x to the n minus 1e to the negative x approaches 0. At x equals 0, the term is 0, so the limit term is 0. Now let's look at the second term. We can pull the constant n minus 1 out of the integral. The remaining integral is exactly the definition of gamma of n minus 1. This proves the recursive relationship. Finally, we can use this to show that gamma of n equals n minus 1 factorial. We start with gamma of n and apply the recursion repeatedly until we reach gamma of 1. We know gamma of 1 is 1. The product of the terms is n minus 1 factorial. This is a beautiful result connecting integrals to combinatorics. Let's conclude with a problem on the volume of a solid of revolution. We are given a curve f of x and asked to find the volume of the solid formed when it's revolved about the x-axis. Part A asks us to explain why the volume is given by the integral from 0 to infinity of 2 pi times f of x squared dx. The standard formula for the volume of revolution about the x-axis is the integral of pi times the radius squared. Here the radius is f of x. The problem statement has a factor of 2 pi. This suggests that the integral is only being taken from 0 to infinity, and the solid is symmetric about the y-axis. If we integrate from negative infinity to infinity, the volume would be pi times the integral of f of x squared. If we integrate from 0 to infinity and double it, we get 2 pi times the integral of f of x squared. This is a common technique for symmetric functions. Now for part B, we need to find the volume of revolution. We substitute the function f of x into the formula. Squaring f of x gives us a over pi squared times the quantity x squared plus a squared. We can pull the constants out of the integral. This simplifies to 2a over pi times the integral from 0 to infinity of 1 over x squared plus a squared dx. The antiderivative of 1 over x squared plus a squared is a standard result. It is 1 over a times arctan of x over a. Now we evaluate the improper integral. This is 2a over pi times the limit as b approaches infinity of 1 over a times arctan of b over a minus 1 over a times arctan of 0. Let's evaluate the limits. As b approaches infinity, b over a also approaches infinity, so arctan of b over a approaches pi over 2. Arctan of 0 is 0. Substituting these values, we get 2a over pi times 1 over a times pi over 2. The a's and pi's cancel out, leaving us with a final volume of 1. This is a remarkable result. The volume of this solid of revolution is always 1, regardless of the value of the constant a. Let's look at one final problem, a real-world application of improper integrals. Bettina is filling a watering can. Water flows in at a constant rate of 6.4 liters per minute. Water leaks out at a rate given by the function R2 of t. We need to find how long it takes for the can to be filled. The net rate of change of water in the can is the inflow rate minus the leakage rate. The net rate is 6.4 minus the expression for R2 of t, which simplifies to 3.9 plus 1.25 e to the negative 0.2 t. The total volume of water in the can at time t is the integral of this net rate from 0 to t. We need to find the value of t for which this integral equals the can's capacity of 16 liters. Let's evaluate the integral. The antiderivative is 3.9t minus 6.25 e to the negative 0.2 t. Evaluating this from 0 to t gives us 3.9t minus 6.25 e to the negative 0.2 t plus 6.25. Now we set this equal to 16 and solve for t. This gives us the equation 3.9 minus 6.25 e to the negative 0.2 t equals 975. This is a transcendental equation that cannot be solved algebraically. We must use a numerical method, such as a graphing calculator. By graphing the function on the left side and the constant 9.75, we can find their intersection point. The solution is approximately t equals 3 Tausend minutes. The question asks for the answer to the nearest second. 3 minutes is 180 seconds, so it takes approximately 3 minutes for the watering can to be filled. Let's look at one final problem, a real-world application of improper integrals. Bettina is filling a watering can. Water flows in at a constant rate of 6.4 liters per minute. Water leaks out at a rate given by the function R2 of t. We need to find how long it takes for the can to be filled. The net rate of change of water in the can is the inflow rate minus the leakage rate. The net rate is 6.4 minus the expression for R2 of t, which simplifies to 3.9 plus 1.25 e to the negative 0.2 t. The total volume of water in the can at time t is the integral of this net rate from 0 to t. We need to find the value of t for which this integral equals the can's capacity of 16 liters. Let's evaluate the integral. The antiderivative is 3.9t minus 6.25 e to the negative 0.2 t. Evaluating this from 0 to t gives us 3.9t minus 6.25 e to the negative 0.2 t plus 6.25. Now we set this equal to 16 and solve for t. This gives us the equation 3.9t minus 6.25 e to the negative 0.2 t plus 6.25 equals 16, which simplifies to 3.9t minus 6.25 e to the negative 0.2 t equals 975. This is a transcendental equation that cannot be solved algebraically. We must use a numerical method, such as a graphing calculator. By graphing the function on the left side and the constant 9.75, we can find their intersection point. The solution is approximately t equals 3 Tausend minutes. The question asks for the answer to the nearest second. 3 minutes is 180 seconds, so it takes approximately 3 minutes for the watering can to be filled. Let's look at one final problem, a real-world application of improper integrals. Bettina is filling a watering can. Water flows in at a constant rate of 6.4 liters per minute. Water leaks out at a rate given by the function R2 of t. We need to find how long it takes for the can to be filled. The net rate of change of water in the can is the inflow rate minus the leakage rate. The net rate is 6.4 minus the expression for R2 of t, which simplifies to 3.9 plus 1.25 e to the negative 0.2 t. The total volume of water in the can at time t is the integral of this net rate from 0 to t. We need to find the value of t for which this integral equals the can's capacity of 16 liters. Let's evaluate the integral. The antiderivative is 3.9t minus 6.25 e to the negative 0.2 t. Evaluating this from 0 to t gives us 3.9t minus 6.25 e to the negative 0.2 t plus 6.25. Now we set this equal to 16 and solve for t. This gives us the equation 3.9 minus 6.25 e to the negative 0.2 t equals 975. This is a transcendental equation that cannot be solved algebraically. We must use a numerical method, such as a graphing calculator. By graphing the function on the left side and the constant 9.75, we can find their intersection point. The solution is approximately t equals 3 Tausend minutes. The question asks for the answer to the nearest second. 3 minutes is 180 seconds. So, it takes approximately 3 minutes for the watering can to be filled. Let's look at one final problem, a real-world application of improper integrals. Bettina is filling a watering can. Water flows in at a constant rate of 6.4 liters per minute. Water leaks out at a rate given by the function R2 of t. We need to find how long it takes for the can to be filled. The net rate of change of water in the can is the inflow rate minus the leakage rate. The net rate is 6.4 minus the expression for R2 of t, which simplifies to 3.9 plus 1.25 e to the negative 0.2 t. The total volume of water in the can at time t is the integral of this net rate from 0 to t. We need to find the value of t for which this integral equals the can's capacity of 16 liters. Let's evaluate the integral. The antiderivative is 3.9t minus 6.25 e to the negative 0.2 t. Evaluating this from 0 to t gives us 3.9t minus 6.25 e to the negative 0.2 t plus 6.25. Now we set this equal to 16 and solve for t. This gives us the equation 3.9 minus 6.25 e to the negative 0.2 t equals 975. This is a transcendental equation that cannot be solved algebraically. We must use a numerical method, such as a graphing calculator. By graphing the function on the left side and the constant 9.75, we can find their intersection point. The solution is approximately t equals 3 Tausend minutes. The question asks for the answer to the nearest second. 3 minutes is 180 seconds. So, it takes approximately 3 minutes for the watering can to be filled.